Right, let's move on to the next part on potentiometer basics. Right, potentiometer, right, essentially is a application of your potential divider circuit, the one with the resistance wire. So we'll look more at it now. All right, let me just click this forward. All right, use my. All right, so what's a potentiometer? Okay, this is a circuit arrangement that's used to measure the PD of power voltage or the EMF of another cell. Okay, so it consists of two parts, a driver circuit and a secondary circuit. So a driver circuit is this portion here, the driver cell that is connected to the uniform resistance wire here. All right, it's over here. So this is called the driver circuit. Right, then you have the secondary circuit. Basically, the secondary circuit is tapped across one end of your resistance wire and then the other one on the sliding contact. So what you put here will depend on your own needs, on the needs of the question over here. All right, so let's look at what we can do here. All right, so moving on, let's go right to the next page. All right, so first thing first, the first application we can have is to use this to determine the unknown EMF of a test cell. Right, so this connection is as such. We have this driver circuit here. All right, same thing. We have the resistance wire from point A to point B, and then you have a sliding contact at point C. Okay, right now what you have here is a galvanometer. Let me just click it forward. Okay, so right now, this portion of the circuit, the one that's connected. Okay, sorry, let me backtrack a bit. All right, so you have this portion here that's forming a secondary circuit. This E naught is the unknown EMF that you're trying to find. All right, and there is some. It's not so important whether there is an internal resistance or not here, but let's just put it here for the sake of it. All right, right now you can see that your secondary circuit is over here, right, over here this way. Okay, then there's a galvanometer here. The galvanometer is supposed to detect whether there's any current. If there's any current being either direction, right, the needle of the emitter will deflect either to the left or right depending on direction of current. Okay, right now because we are tapping the secondary circuit across A and point C, right? Essentially, what's happening here is that this point A is at higher potential than point C. So what is happening here is you have what you're trying to set up here is that you have essentially another cell here that is equivalent to VAC, and this cell is such that this potential difference here is such that because A is a higher end and then C is at the lower end, so it's pointing to the right hand side. The positive is pointing to the left hand side, and you can see that it's directly opposite your E naught. Okay, so in this case here, right, which if you consider the secondary circuit, the current can flow in either direction depending on the current can either flow clockwise and clockwise depending on which is bigger. Let's just click on. So I can adjust VAC by moving the sliding contact. So if I slide this more to the left, VAC will be smaller. I slide more to the right, VAC will become bigger. Okay, so since VAC and E naught are connected in opposite polarities, adjust VAC until galvanometer has null deflection, no current flow. All right, so this is what we can do. We can set it up this way, and then we can see which one has the bigger potential difference, right? So what I'm trying to do is that if I make this too small, if I make my VAC too small, if it's smaller than E naught, then current will flow in this direction, will flow across from the right hand side of the galvanometer to the left hand side of the galvanometer. But if I set my VAC to be too big, current will flow in the opposite direction. So it come down and flow through here, then the galvanometer will deflect to the right hand side. So my aim is to set it such that the galvanometer does not deflect at all. So when it doesn't deflect, there's no current flow. If there's no current flow, my VAC matches E naught now, right? Okay, so this is the formula I have because I can set my E naught to be, my VAC to be equal to E naught, and that will occur at this particular length of LAC, where I can use this to find ratio. So if I know the length, I can work out what is my E naught here. Okay, note that earlier we mentioned that there's this internal resistance in the diagram here, but does the value of R really matter here? Okay, because we look carefully, if my two potential differences are the same, this VAC and this E naught is the same, right? No matter how small this internal resistance is, right, there's no current flowing because your net EMF will be 0. Okay, but if you have, even if you if you have a difference, but this R is significant, right? Because our galvanometer is very sensitive, it will still be able to detect a small current, even if you have a very, very small EMF and a very small and a very large resistance that will result in a small current, right? So the galvanometer will still deflect, right? So the value of R doesn't really matter here, which is the interesting thing about this way of doing to measure the test cell's EMF. All right. Okay, so now we're going to move on to what's the advantage of the potentiometer over a voltmeter or digital multimeter. All right, so far we have been usually dealing with an ideal voltmeter. Okay, what exactly is an ideal voltmeter? It's one with infinite resistance. Okay, so here I've done essentially the same setup, just that one has a voltmeter infinite resistance, the other one has one with finite resistance. So that means this resistance here is a value that is finite, that is basically not infinity lah, which is just a value of R. Right, so let's see what I can do here. Okay, first, okay, so of course, in this case, my ideal voltmeter has a resistance of infinity. Okay, then my current coming out from the 6-volt cell will go in this direction, and then when it comes to junction B, right, all of it will flow through resistor Y. None of it will flow through resistor, the voltmeter. Okay, this is important because I want the entire current to go through my resistor here. Okay, because the reason is this. Okay, compared to this one over here, right, on the right hand side where my voltmeter has a finite resistance, right, that means it's not big enough, right. Some of the current will go through the voltmeter, right. So this voltmeter's current reading, if I have to place an ammeter here, be more than 0, and then this reading here will be less than I naught. Okay, what's the issue with this over here, right? If you go on to the next slide, I think this will be a bit better in explaining to you. All right, if we set this up this way, if I have an infinite infinite resistance voltmeter here, right? What I'm doing here is, okay, my voltmeter will read, okay, the voltmeter is reading the PD across the terminal voltage, right, across the terminal ends of the cell, which includes your internal resistance. So this will be resistance of voltmeter over resistance of voltmeter plus internal resistance multiplied by E. If RV tends to infinity, right, this whole expression will tend to 1. And then essentially it will be equals to E lah. The voltmeter will read the EMF. And then we just double check if we take the voltmeter, if we're able to measure the potential difference across R, this is what we'll get. We get R over RV plus R. But because R is very, very small compared to RV, right, this whole expression will tend to 0. Alright. And then the problem when we're dealing with a finite resistance voltmeter, right? If you do it this way now, we same thing, we do RV over RV plus R times E. This value here is smaller than E. Alright. And then do the same for the internal resistance. The potential difference across internal resistance will not be 0. So some of the potential drop occurs across the internal resistance if your voltmeter does not have a large enough resistance. Okay, this is based on your potential divider concept. Alright. Okay, so to backtrack a little bit, okay, so this is why in this case, right, your potentiometer setup is much better. We just backtrack to the slide over here. This potentiometer setup, right, does not make use of a voltmeter. Okay, it's just because you have a because in reality, right, all your voltmeters do not have infinite resistance. You will lose some of the potential difference across the internal resistance instead. By this setup here, as long as my VAC is equals to my E naught, I will be able to get no current flowing. Okay, conversely, as long as the difference between VAC and E naught, right, I will get a current flowing, right, regardless of the value of resistance here. Okay, so that's all I have for this section. We will move on to next section. We will move on to the applications of your potentiometer.